Alright, in this video we will continue our discussion of the Bernoulli principle and see how it can be applied to understand such things as curveballs, fastballs, and other types of things such as aerodynamic lift. I remind you from the past video that the pressure plus 1/2 the density times the speed squared plus the density times g times the y height has to equal a constant for an ideal fluid. This is Bernoulli's equation. Now, again, this is like the negative work per volume done externally upon the fluid. This is the kinetic energy per volume of the fluid at that point. This is the gravitational potential energy per volume of the fluid at each particular point. Now, a lot of times, many times, the problem involves something where the object, for all intents and purposes, does not have a great change in y. And so we're simply going to ignore, for instance, that the object has very small y changes. This term will be very small, changing when we go from one side of the object to the other in a fluid, and so we simply ignore this. This is like saying that if you have an object, say here, on a table, and it moves to some other point, say over here, because you're applying some force, F. That table may not be perfectly level. It might be 3 millimeters up. But if the change in gravitational potential energy is very small, because it's almost flat, then we can just ignore gravitational potential energy, and the work here is totally going into changing the kinetic energy. And that's what we have here. Now, let's look and apply this, because what's interesting, if this has to be constant, if this term goes up, it implies that that term has to go down to keep this constant. And that says that if the fluid moves faster, the pressure at that point of the fluid, and hence the pressure it applies to anything that touches it, such as a container, airplane wing, baseball, or whatever, must decrease. Let's see if we can use that to show why an airplane flies and why the shape is the way it is. Let's take an airfoil. And I'll take an airfoil the way they're built for planes. An airfoil often has a shape of something like this. Furthermore, airplanes like to fly into the wind, which seems kind of strange. But from the frame of reference, for the sake of the airplane, the wind is what's moving and the airplane is stationary. This wind goes up and over. This one goes over like this. This goes straight across. And this goes like so. The air makes this trip at the same amount of time that the air below it makes this trip. But it has further to cover. And since it has to go further, it must be traveling faster. So this is the faster air, and this is the slower air. Now what we just learned was the faster air has the lower pressure. So that means this P here is lower than the pressure applied by the bottom air up. And when you multiply that pressure times the area, if you shape this right, that means it'll have a lower force. So there'll be an upward force. It's known as aerodynamic lift. And this is what enables the plane to get up. Now, if you were not moving, if they're sitting stationary and there's really no airflow, then The air basically is in, with no motion, has little or no lift. And therefore you want to have the air going fast. So you need to get a certain speed to get this air going. And it helps if the air is being blown so it has speed anyway. If you're going in your reference frame, you're not going. The air's going. If the air is blowing across you even when you're stationary, then it has velocity, and those two velocities can add. So you want to go into the wind to make the relative velocity greater rather than away from the wind, which would make the relative velocity less. And this is why they turn into the wind to take off and get the maximum upward force, especially on things, for instance, like an aircraft carrier where you have a limited distance to get off the deck before you'll crash into the water. There are airfoils used in other places. For instance, if you've seen anything in a race car, race cars build their foils on the back of these, like Le Mans cars. So you have this car like this, and they attach these things, obviously not drawn to size, but they take these things in the back, but they look upside down. Well, that's exactly right. They are upside down. And the reason is now you want the air to go like this, and the air going this way you want to go like that. And the net effect of that is a downward force. That downward force causes the normal force to go up, but the friction force is proportional to the normal force. So as you push down, the normal force goes up, the friction force goes up. And you need the friction force in order to make turns and to have good traction. So the idea is to push down on the car. Otherwise, the air going under the car with the shape the car has, where you're trying to cut down drag, also tends to make the car want to lift. And as it lifts, it has less normal force, and you lose your friction force for making turns. So they'll design, especially in Grand Prix type cars, these downward so that they can go higher speeds. These are lighter weight cars, higher speed. You don't see this with NASCAR, where you got a much heavier car and you're going at a much lower speed. Now let's look at the case of a baseball, and we'll look at a fastball. So fastball has laces, which are very important, but my primary discussion here is going to be about spin and how it changes the relative velocity on the baseball. The baseball, let's assume, is going this way, and if it's a fastball, for instance, it will have backward spin because of the way the ball is released from the fingers of the pitcher. In the baseball's frame of reference, it is not moving. It is the air that is moving, and the air is going in the opposite direction than the way the batter sees the baseball. So if the fastball is going this way, from the ball's perspective, the air is running into it in the opposite direction. Now what we need to do is look at how this arrow connects with this arrow of spin. When the wind comes in and connects with the laces and goes in the same direction of the spin, the net effect is to add velocities, making the wind have a bigger V. On this side, you have a velocity of the ball going like that. The net effect of that is to oppose this, which makes a smaller velocity of the air. So this is V lower, and this is V higher. Again, it has to do with the relative velocity of the surface with respect to the wind. When they add together, it has a higher one. When they go in the opposite way, it has a slower one. Now, because this is a higher velocity than down here, that means that the downward push is less than the upward push. So PU is greater than P down. So we get a net lift. If you were to spin the ball the opposite way, you would get a net downward. It's called a drop ball or sinker. So having a fastball that spins gets you an upward lift. What's necessary? Well, one is, of course, how fast this air goes. So the faster and harder you can throw, the better motion you'll have on your fastball. The placement of the laces is important in how you get a good spin. And last but not least is good spin. So if you overthrow the ball, if you hold it too tight, and you don't get good rotation, you don't get good motion on your fastball, it doesn't move much, it tends to go pretty straight. Now, it should be noted that a real baseball follows a parabolic path. The net effect of this lift is not to make it go like that. To do that, you need 10,000 RPMs. 10,000 revolutions per minute, and no human being can throw a baseball. It just doesn't have enough surface area. Remember, this is pressure, but we got to find force, and the force has to exceed gravity, and we still have gravity pulling it down. So what really happens is that the baseball follows a less curved path for a really good pitcher. Now, the batter, over years, has trained himself to see that curved parabolic path as straight. And so when he swings, he actually swings under where he sees the ball. He doesn't think that way, but that's what he does. The net effect of this is to make it not fall as far. So the batter swings expecting the ball to be here. The ball is there, and he says the ball is risen. The ball is not risen. The ball is actually just not fall as much. Now, if you throw a softball, because it can be thrown from a shorter distance, has a much larger surface area, you can actually get a true rising fastball. But a baseball truly cannot rise. And likewise, when a third baseman throws a ball over to first base, and people talk about throw it on a line, you don't throw it on a line. Nobody can throw it on a line. There's gravity. It's falling. In fact, in Little League, you're basically the Little League player at third base is throwing it about 3 foot over the first baseman's head in order to make it fall correctly at the first base. But if you told the kid to throw it 3 foot overhead, he'd throw it 6 feet over the head. All right, so we've already adapted to this curved path. There are many other cases where Bernoulli's principle is important. We also don't just have to do the one about velocity. We could, of course, go back up here and we could talk about times in which, for instance, we have a tank or something, and there's a hole in the tank, and the pressure here is P naught, and the pressure here is P naught. The volume, if this is a big tank, the velocity up here, V1, would be 0. The velocity here, because it comes spewing out, would not be 0. And what we could get is P naught plus 1/2 rho V1 squared, but that's 0, plus rho G H, Y1, I don't know why I wrote H, my fault, is equal to P naught plus 1/2 rho V2 squared plus rho G Y2. The pressures cancel, and we get 1/2 rho V2 squared is equal to rho G Y1 minus Y2. The rho's will cancel. V2 squared will be 2 times, cancel the wrong thing, cancel the rho, not the G. 2G Y1 minus Y2. This looks like a falling ball. Well, of course, came out of energy analysis. So it's the square root of 2GH. This was done by a guy by the name of Torricelli, and hence it's often called Torricelli's principle. All right, that finishes this discussion of Bernoulli.